Hi, my name is Yuriy and I'm a Maths PhD student at Imperial College London as well as a tutor at the Elite Prep. Today I'm going to be walking through another classical quantum research interview problem, and the problem I'm going to be going through is called the 3 consecutive heads problem. Without further ado, let's introduce it. Given a fair coin, what is the expected number of throws until we see 3 consecutive heads? And the extension to this is, what about n consecutive heads? So as an example, we could throw tails, heads, tails, tails, heads, heads, heads. And this sequence is 7 steps long, finishing with heads, heads, heads. So in this case, we needed 7 steps to get 3 consecutive heads. So notice that we have to restart every time we throw a tail. So even if we throw 2 heads in a row, as soon as we throw a tail, we then have to start all over again. And that is something which commonly causes issues for people first tackling these kinds of problems. But luckily we do have a technique to deal with these, and that is going to be the hint for this problem. The hint is just to use the Markov chain technique. If you haven't tried this question already, I urge you to try it now. If you've already tried it, then let's continue. So the concept of a Markov chain is to reconstruct our problem as a bunch of states with transition probabilities from those states. So the hardest part here is to really know what each state should mean. I'll do this by going through this example. So let's have 4 states in this scenario. And let's also label these states as 0, 1, 2, and 3. So at each point in time, time being the throw on which we are. So if we're at throw 1, if we've just thrown throw 1, we're at time 1. If we've just thrown throw 2, we're at time 2, and so on. So we can label them like this: 1, 2, 3, all the way up to 11. We can also add time 0, which is before we've thrown anything. And 0, 1, 2, 3 here represent the state at which we are on. And the state tells us how many consecutive heads we've seen up until now. So for example, at time 0, we've not seen any, so we've not seen any heads at all because we haven't thrown anything. So at time 0, we're at state 0. At time 1, we have thrown 1 tail. So at time 1, we've still seen 0 heads. At time 2, we've finally seen 1 head, and we've seen 1 consecutive head because at time 1 there was a tail. So we've only seen 1 head at time 2. So then we're at state 1. At time 3, we have now seen head, head. But before that we had a tail. So then we're at state 2. But then at time 4, we see a tail again. So we're now back at state 0 because we saw a tail and the sequence of heads is terminated. So this then kind of paints a picture as to what we should do for these states. So once you've written the states, we want to fill in the transition probabilities for each of these states. And the question can be rephrased as follows. If we start at state 0, what is the expected number of steps to reach state 3? Because state 3 represents that we have thrown 3 consecutive heads. So this is exactly the situation that we want. So let us just fill in the transition probabilities for each state. So a transition probability is defined as the probability in one time step of moving from one state to another state. So for example, we cannot go from state 0 to state 3 in one time step, because you can't go from having thrown 0 consecutive heads to 3 consecutive heads in one throw. So we need to fill in all the possible transitions. So one possible transition is going from 0 back to 0. That happens with probability 1/2 if we throw a tail. 0 can also go to 1 by throwing one head. And that again happens with probability 1/2. 1 can go to 2 with probability 1/2 if we throw another head after already being on state 1, or it can go back to 0 if we throw a tail. Then 2 can go to 3 with probability 1/2, or it can go back to 0 with probability 1/2, because if we throw a tail at the point that we have 2 consecutive heads, we then have 0 consecutive heads. And finally, when we're on state 3, we already have 1. So we've got the required situation. So we can just say that at this state, we don't do any more, and this recurs with probability 1. So now we want to compute the expected number of steps until we reach state 3 from state 0. So let us introduce a new variable, call it EI. And EI denotes expected number of throws until state 3 is reached from state I. Okay. So then we can start computing each of E3, E2, E1, and E0 in terms of the states which it transitions to. So for example, E3 is very easy. E3 is just 0, because if we're already at state 3, then we don't need any more steps to reach state 3. So this is just 0. E2, well, for this we need to look at the state that we're on. So if we're at state E2, we can either, with probability 1/2, which takes one step, go to step 3. So we either have 1/2 probability of taking one step plus the number of steps that we need at step 3 to reach state 3. And 2 can also go back to 0 with probability 1/2. So it also can do 1/2, one step plus E0, which is the number of steps required to get to E3 from 0, which is just equal to 1 plus 1/2 0 plus 1/2 E0. E1 is computed similarly, and E0 is 1 plus 1/2 E0 plus 1/2 E1, because E0 could have gone back to itself with probability 1/2, or E0 could have gone to state 1 with probability 1/2. So now the question boils down to solving these equations simultaneously. Going through this computation, we have, and then after we have these formulae, we can find E0, because E0 was the expected number of steps to reach state 3 from state 0. So therefore, the expected number of steps is 14. An adaptation of this question is to consider how many throws have to be taken to get n consecutive heads. So again, in this case, we would have to construct a Markov chain. You don't have to draw it out every time, but for the purposes of the presentation, we can. So this is state n minus 1, this is state n, this is state 0. And we again have transition probabilities of 1/2 forwards and also of 1/2 returning to 0. So in this case, we can use a similar formulation. So EI as before, I equals 0 up to n, and En is equal to 0 this time, because at state n, we've already thrown n consecutive heads, so we don't need to take any more steps. So from state n, it takes 0 steps to get to n consecutive steps. Then we can write an iterative formula. En is equal to 1 plus 1/2 En plus 1, because there's a half probability of throwing one more head. If we throw one more tail, then we reset. So if we throw one more tail, we have E0. But then for this formula for En, we can also do the following. We know that En minus 1 is actually equal to 1 plus 1/2 En plus 1/2 E0. So therefore, taking the second equation from the first, we have, and this can be used to construct a telescoping sum. So if we consider En minus E0, that's just equal to the following telescoping sum. And then we have a formula for this, because En plus 1 minus En is just equal to 2En minus En minus 1, and that's equal to 2 to the n E1 minus E0. So this is equal to the following simplified form. However, we can now look at state 0, and at state 0 we can go with half probability to state 1 and with half probability back to state 0. So therefore E0 is equal to 1 plus 1/2 E0 plus 1/2 E1, just as before. And that means that E0 equals 2 plus E1 by rearrangement. Substituting this in means that we have equals minus sum from n equals 1 to n of 2 to the n, because this was just equal to minus 2, and also En was equal to 0. So therefore E0 is equal to sum from n equals 1 to n of 2 to the little n. And that is the solution for the general case of n heads in a row. Thank you for watching. I hope to see you in the next one.